Hilbert's paradox of the Grand Hotel is a thought experiment which illustrates a counterintuitive property of infinite sets. It is demonstrated that a fully occupied hotel with infinitely many rooms may still accommodate additional guests, even infinitely many of them, and that this process may be repeated infinitely often. The idea was introduced by David Hilbert in a 1924 lecture and was popularized through George Gamo's 1947 book 123, Infinity. The paradox. Consider a hypothetical hotel with a countably infinite number of rooms, all of which are occupied. One might be tempted to think that the hotel would not be able to accommodate any newly arriving guests, as would be the case with a finite number of rooms, where the pigeonhole principle would apply. Finitely many new guests. Suppose a new guest arrives and wishes to be accommodated in the hotel. We can move the guest currently in room 1 to room 2, the guest currently in room 2 to room 3, and so on, moving every guest from his current room n to room n+1. After this, room 1 is empty and the new guest can be moved into that room. By repeating this procedure, it is possible to make room for any finite number of new guests. Infinitely many new guests. It is also possible to accommodate a countably infinite number of new guests. Just move the person occupying room 1 to room 2, the guest occupying room 2 to room 4, and, in general, the guest occupying room n to room 2n, and all the odd-numbered rooms will be free for the new guests. Infinitely many coaches with infinitely many guests each. It is possible to accommodate countably infinitely many coachloads of countably infinite passengers each, by several different methods. Most methods depend on the seats in the coaches being already numbered. In general, any pairing function can be used to solve this problem. For each of these methods, consider a passenger's seat number on a coach to be, and their coach number to be, and the numbers are then fed into the two arguments of the pairing function. Prime powers method. Empty the odd-numbered rooms by sending the guest in room to room, then put the first coach's load in rooms, the second coach's load in rooms. For coach number we use the rooms where is the odd prime number. This solution leaves certain rooms empty, specifically, all odd numbers that are not prime powers, such as 15 or 847, will no longer be occupied. Prime factorization method. You can put each person of a certain seat and coach into room. Because every number has a unique prime factorization, it's easy to see all people will have a room, while no two people will end up in the same room. For example, the person in room 2592. Interleaving method. For each passenger, compare the lengths of an as written in decimal. If either number is shorter, add leading zeros to it until both values have the same number of digits. Interleave the digits to produce a room number. Its digits will be first digit of coach number, first digit of seat number, second digit of coach number, second digit of seat number, etc. The hotel guest in room number 1729 moves to room 01070209. The passenger on seat 1234 of coach 789 goes to room 01728394. Unlike the prime powers solution, this one fills the hotel completely, and we can extrapolate a guest's original coach and seat by reversing the interleaving process. First, add a leading zero if the room has an odd number of digits. Then interleave the number into two numbers. The seat number consists of the odd number digits and the coach number is the even-numbered ones. Of course, the original encoding is arbitrary, and the roles of the two numbers can be reversed, so long as it is applied consistently. Triangular number method. Those already in the hotel will be moved to room, or the triangular number. Those in a coach will be in room, or the triangular number, plus. In this way all the rooms will be filled by one, and only one, guest. This pairing function can be demonstrated visually by structuring the hotel as a one-room deep, infinitely tall pyramid. The pyramid's topmost row is a single room, room 1, its second row is rooms 2 and 3, and so on. The column formed by the set of rightmost rooms will correspond to the triangular numbers. Once they are filled, the remaining empty rooms form the shape of a pyramid exactly identical to the original shape. Thus, the process can be repeated for each infinite set. Doing this one at a time for each coach would require an infinite number of steps, but by using the prior formulas, a guest can determine what his room will be once his coach has been reached in the process, and can simply go there immediately. Arbitrary enumeration method. Let is countable since is countable, hence we may enumerate its elements. Now if, assign the th guest of the th coach to the th room. Thus we have a function assigning each person to a room. Furthermore, this assignment does not skip over any rooms. Further layers of infinity. Suppose the hotel is next to an ocean, and an infinite number of car ferries arrive, each bearing an infinite number of coaches, each with an infinite number of passengers. This is a situation involving 3 levels of infinity, and it can be solved by extensions of any of the previous solutions. The prime factorization method can be applied by adding a new prime number for every additional layer of infinity. The prime power solution can be applied with further exponentiation of prime numbers, resulting in very large room numbers even given small inputs. For example, the passenger in the second seat of the third bus on the second ferry would raise the second odd prime to 49, which is the result of the third odd prime being raised to the power of his seat number. This room number would have over 30 decimal digits. The interleaving method can be used with 3 interleaved strands, instead of 2. The passenger with the address 232 would go to room 232, while the one with the address 4935-198-82217 would go to room number 008, 402,912,391,587. Anticipating the possibility of any number of layers of infinite guests, the hotel may wish to assign rooms such that no guest will need to move, no matter how many guests arrive afterward. One solution is to convert each arrival's address into a binary number in which ones are used as separators at the start of each layer, while a number within a given layer is represented with that many zeros. Thus, a guest with the prior address 25131 would go to room 10,10,10,10,100,010. As an added step in this process, 1 zero can be removed from each section of the number. In this example, the guest's new room is 101,011,001. This ensures that every room could be filled by a hypothetical guest. If no infinite sets of guests arrive, then only rooms that are a power of 2 will be occupied. Infinite layers of nesting. Although a room can be found for any finite number of nested infinities of people, the same is not always true for an infinite number of layers, even if a finite number of elements exists at each layer. For example, suppose some people arrive in a set of spaceships which are nested in accordance to the following rules. The smallest ships, each 100 cubic meters in volume, contain 10 people. After this, every ship is grouped with 9 other ships of the same size. Inside a mothership exactly 100 times the volume of each of its 10 daughter ships. All ships of the same size are isomorphic to one another. For example, each 1 million cubic meter ship contains exactly 10,000 cubic meter ships, each of which contains exactly 10 100 cubic meter ships, each containing 10 people. This extends upward infinitely, so that there is no largest ship. A given passenger's address in this system would be infinite in length, corresponding to the decimal form of one of the real numbers ranging from 0 to 1. Exactly one guest would have the address corresponding to 1/6, for example, and another to the value of pi-3. The set of real numbers, and the set of guests in this example, is uncountably infinite, because no one-to-one pairing can be made between countable and uncountable sets. Rooms at the hotel cannot be made for all of these guests. although any countably infinite subset of them can still be accommodated. For example, the set of guests whose addresses terminate in an infinitely repeating sequence, corresponding to a rational number. If this variant is modified in certain ways, then the set of people is countable again. For example, suppose there were a largest ship, directly containing a finite number of both ships and people, and each of these ships in turn contained both ships and people, and so forth. This time, any given person is a finite number of levels down from the top, and thus can be identified with a unique finite address. The set of people is countable again, even if the total number of layers is infinite, because we do not have to consider an infinite layer in either direction. Analysis. Hilbert's paradox is a veridical paradox. It leads to a counterintuitive result that is provably true. The statements, "there is a guest to every room," and "no more guests can be accommodated," are not equivalent where there are infinitely many rooms. An analogous situation is presented in Cantor's diagonal proof. Initially, this state of affairs might seem to be counterintuitive. The properties of infinite collections of things are quite different from those of finite collections of things. The paradox of Hilbert's Grand Hotel can be understood by using Cantor's theory of transfinite numbers. Thus, while in an ordinary hotel with more than one room, the number of odd-numbered rooms is obviously smaller than the total number of rooms. However, in Hilbert's aptly named Grand Hotel, the quantity of odd-numbered rooms is not smaller than the total number of rooms. In mathematical terms, the cardinality of the subset containing the odd-numbered rooms is the same as the cardinality of the set of all rooms. Indeed, infinite sets are characterized as sets that have proper subsets of the same cardinality. For countable sets, this cardinality is rephrased. For any countably infinite set, there exists a bijective function which maps the countably infinite set to the set of natural numbers, even if the countably infinite set contains the natural numbers. For example, the set of rational numbers, those numbers which can be written as a quotient of integers, contains the natural numbers as a subset, but is no bigger than the set of natural numbers since the rationals are countable. There is a bijection from the naturals to the rationals. The Grand Hotel Cigar Mystery. Another story regarding the Grand Hotel can be used to show that mathematical induction only works from an induction basis. Suppose that the Grand Hotel does not allow smoking, and no cigars may be taken into the hotel. Despite this, the guest in room 1 goes to the guest in room 2 to get a cigar. The guest in room 2 goes to room 3 to get 2 cigars, one for himself and one for the guest in room 1. In general, the guest in room N goes to room to get N cigars. They each return, smoke one cigar and give the rest to the guest from room. Thus, despite the fact no cigars have been brought into the hotel, each guest can smoke a cigar inside the property. The fallacy of this story derives from the fact that there is no inductive point from which the induction can derive. Although it is shown that if the guest from room N has N cigars, then both he and all guests in lower numbered rooms can smoke. It is never proved that any of the guests actually have cigars. Therefore, it does not follow that any guest can smoke a cigar inside the hotel. The fact that the story mentions that cigars are not allowed into the hotel is designed to highlight the fallacy. However, since there is an infinite number of rooms in the hotel and each guest must go to guest for his cigar, this process of going up one room never ends and no cigars are ever smoked.